Okay, here what we're going to do now is that we're going to expand upon our last video and we're going to learn about symmetry tests. And these are the ways that we can determine algebraically whether or not our functions or our equations have any type of symmetry. So first of all, let's analyze this function f of x is equal to x squared. So in our last video, we already determined that this function f of x has symmetry with respect to the y-axis. So we already determined graphically that this function has symmetry with respect to the y-axis. I'm going to make a little note here. I'm going to make a little note in blue. Note that f of x is in fact a function. So f of x is in fact a function. So let's go ahead and describe test to determine y-axis symmetry. So the test will follow the following directions. Every time you have an x plug in negative x, if this resolves to the original equation, your equation has y-axis symmetry. And you could also put in here your graph has y-axis symmetry. So it depends on which way you want to analyze this, whether it be graphically or algebraically. So we can see that we're going to determine our y-axis symmetry by plugging in a negative x every time you see an x. So notice here we have f of x equals to x squared, and that's the same thing as me writing y equals to x squared. F of x is the functional notation, and y is just the linear notation. So if we want to test for y-axis symmetry, we're going to plug in negative x for all values of x. So negative x for all values of x. So here we're going to have y equals to negative x squared. And whenever I square a negative, I know I'm going to have a positive. And this is the exact same as the original. Exact same as the original. Therefore, we know that we have y-axis symmetry. We have y-axis symmetry. So let's go ahead and try this on a different example. Let's go ahead and actually talk about symmetry with respect to the symmetry with respect to the x-axis. So in the last example, we analyzed x equals to y squared. I'm going to make a little note over here. Note, this equation is not the equation of a function. This equation is not the equation of a function because what we have is that we have this graph that opens to the right, and clearly if I draw a vertical line, through this graph, it intersects more than once, which violates the vertical line test, and we know we do not have a function. So the rule that we're going to use to test for x-axis symmetry is every time you see a y, plug in negative y. If this resolves to the original equation your graph has x-axis symmetry. So looking at this, if we look at this example, x equals to y squared, and we test for x-axis symmetry, we're going to plug in negative y for all values of y. So we're going to have x equals to negative y squared, and whenever we square a negative, we get a positive, and notice this is the original. Therefore, we have x-axis symmetry. But recognize this circumstance that if we do have x-axis symmetry, we will not have a function. And this actually will lead when we talk about the next portion of the section in regards to even and odd functions. This actually is an indicator of whether or not you have an even function, an odd function, or neither even or odd. But we'll expand on that in our next couple videos. But for right now, this example does not have any y-axis symmetry. However, it does have x-axis symmetry, and we showed it using this rule. In order to test for our last type of symmetry, we're going to test for symmetry with respect to the origin. Symmetry with respect to the origin. So the rule states plug in negative x for all values of x, and negative y for all values of y. If this resolves to the original, your graph has origin symmetry. And that's the same thing as me saying symmetry with respect to the origin. So either way is fine. So let's go ahead and analyze that original function we had, which was f of x equals to x cubed. And again, I'm going to make that note over here. And note f of x equals to x cubed is in fact a function. So notice functions that have symmetry with respect to the origin, functions also will have symmetry with respect to the y-axis. However, if a graph has symmetry with respect to the x-axis, it will not be a function. And as we progress through, that's very important for us to remember. So now let's go ahead and replace, to make this easy on ourselves, let's replace f of x in terms of y and let that be equal to x cubed. It just makes that a little bit easier for this section. And now our rule states every time we see every time we see positive x, we plug in negative x. Every time we see positive y, we plug in negative y. So we're replacing both our x and our y variables with the negations of the x and y variables. So we will have negative y equals to the quantity of negative x cubed. Negative y will stay negative y, and negative x cubed becomes a positive x cubed. It stays negative x cubed, and negative raised to the third power is in fact negative. But when I divide both sides through by negative 1, I get y equals to positive x cubed, and this in fact is the original. Therefore, we know we have symmetry with respect to the origin.